Alright guys, welcome back to Underground Science, and if you just came back from the Glycolysis Part 1 video, you would know that we left off right here, okay? So we left off talking about how aldolase, our enzyme that splits the crap out of fructose 1,6-bisphosphate, right, which is right here, this 6-carbon structure right here. So aldolase splits fructose 1,6-bisphosphate into dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. All right, and from here, one important thing to say, right, everything that's going to be produced, like everything, is going to be 2 of each, okay, because we'll see later, actually. I think it'll make more sense if we explain it later. Okay, so now, for right now, let's just focus on what happens to glyceraldehyde 3-phosphate, and let's come back to dihydroxyacetone phosphate later. All right, so let me go ahead and just erase all these arrows real quick so we can come back to it and discuss what happens to dihydroxyacetone phosphate. And that'll make sense after we discuss that. It'll make sense why there's 2 of each, okay, when we start glyceraldehyde 3-phosphate. Start from this process. So now we have glyceraldehyde 3-phosphate, okay? And glyceraldehyde 3-phosphate is going to be converted into 1,3-bisphosphoglycerate, which is right here. So we go from glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate. And one thing we see here is that the enzyme catalyzing this reaction from glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate is glyceraldehyde 3-phosphate and then dehydrogenase, right? So that's pretty easy to remember. All right, and another thing we see is that NAD plus is getting reduced to NADH, which is right here. We see that in this reaction right here. All right, so, and all reduced means that we're just gaining electrons. So previously, right, let me just go ahead and write this zoomed in right here. So what this says is that we're putting NAD plus in the reaction and we're getting out, or what, actually let's write this as capital because that's what it is. We're putting in NAD plus, and NAD plus is actually getting reduced, okay, in this step. And why is it getting reduced? Because it's gaining electrons. As we can see, it's gaining electrons because originally it had a formal charge of +1, right? So it had 1 less electron, and then we gained electrons to make it to NADH. Okay, so it lost that +1 formal charge, means it got more negative. So we gained electrons. All right, so that's that. Then from 1,3-bisphosphoglycerate, guys, we went to 3-phosphoglycerate. And in this step, what happened was we used ADP and a phosphate to make ATP. All right, so we made an energy molecule here. So ATP was made because we used an inorganic phosphate and adenosine diphosphate, and we converted it into adenosine triphosphate. Where, right, in the step for 1,3-bisphosphoglycerate to 3-phosphoglycerate. In that step, we made an ATP molecule. Okay, and the enzyme catalyzing this step from 1,3-bisphosphoglycerate to 3-phosphoglycerate is phosphoglycerate kinase. All right, and that's pretty much what's happening in this step. And this phosphate that you see here on the 1 carbon came from just a regular free-floating phosphate in the cytoplasm. Okay, and next, from 3-phosphoglycerate, we went from 2 to 2-phosphoglycerate. That's pretty easy to remember, right? 3 to 2, and phosphoglycerate stays the same. So we still have a 3-carbon phosphate, still a 3-carbon sugar, sorry, or not a sugar, 3-carbon molecule, because sugar is broken down, right? 3-carbon sugar, or a molecule, to 2 or 3-carbon molecule still, but what changed is that the phosphate went from the 3-carbon to the 2-carbon. Okay, so 3-carbon molecule, 3-carbon molecule, which is the same, but now we call it 2-phosphoglycerate instead of 3-phosphoglycerate because the phosphate's on the 2-carbon. And the enzyme that we use to convert 3-phosphoglycerate to 2-phosphoglycerate is phosphoglycerate mutase. All right, and the second to last step, so we go from 2-phosphoglycerate to phosphoenol pyruvate. And a good way to remember what enzyme was used is, you see the enol here, so we can remember that as enolase is being used to convert from 2-phosphoglycerate to phosphoenol pyruvate. And in this step, we see a molecule of water is lost. All right, and the phosphate is still on the 2-carbon here. Okay. Lastly and finally, right? This is what we've been waiting for. Phosphoenol pyruvate is converted into pyruvate. And I didn't write the enzyme down, so let me go ahead and write it down. What enzyme is catalyzing this reaction for the conversion of phosphoenol pyruvate to pyruvate? Well, this enzyme is going to be called pyruvate kinase. All right. And so finally, this was the structure all along that we were trying to produce for glycolysis. Okay, and in this step, we again make an ATP molecule from ADP and an inorganic phosphate. All right, so finally that happened, right? And now let's talk. So right now, all this time we've been saying 1 molecule of water is lost. We've been saying 1 molecule of phosphoenol pyruvate is produced, 1 molecule of 2-phosphoglycerate is produced, 1 molecule of 3-phosphoglycerate, right? All that, 1 molecule of pyruvate is produced. But in reality, all these 1 molecules are actually 2 molecules, because all this is happening because glyceraldehyde 3-phosphate is getting converted into all this. What about dihydroxyacetone phosphate, right? We can't just leave this out of the party, right? Dihydroxyacetone phosphate can't go from dihydroxyacetone phosphate into 1,3-bisphosphoglycerate like glyceraldehyde 3-phosphate can. It has to get converted to glyceraldehyde 3-phosphate first. And then again, all the reactions that we saw here will happen again because of dihydroxyacetone phosphate being converted to glyceraldehyde 3-phosphate. All right, so when dihydroxyacetone phosphate gets converted to glyceraldehyde 3-phosphate, we use the triose phosphate isomerase enzyme to convert from dihydroxyacetone phosphate to glyceraldehyde 3-phosphate. And then again, once dihydroxyacetone phosphate is converted to glyceraldehyde 3-phosphate, we're going to see all these reactions happen one more time, which is why all the molecules being produced is 2 of each, not 1, because it's happening again, right? So instead of 1 ATP being produced here, there's actually 2 ATP being produced. All right, just like that, instead of 1 water molecule being lost, there's 2 water molecules being lost. And again, same thing, instead of 1 ATP being produced, there's 2 ATP being produced. And again, instead of 1 pyruvate being produced, there's 2 pyruvates being produced. All right, so glucose is a 6-carbon sugar and it's split into 2 3-carbon sugars, or not a sugar, 2 3-carbon molecules, all right, which are 2 pyruvates. That was the whole goal of glycolysis, to split sugar or glucose into 2 smaller particles, or not particles, 2 smaller molecules, which are pyruvates. All right, and same thing here actually, which I didn't write down. It's pretty small, you can't see it, but remember the NAD plus being reduced to NADH? Well, there's not 2 NADH being made, or there's not 1 molecule being made. Like it's shown, there's 2 NADHs being made. All right, so there's 2 NAD pluses being reduced to 2 NADHs. All right, so let's go ahead and write down what we just said. So we said that we have 4 ATPs being made, right? We have 4 ATPs being made in this whole, from glyceraldehyde 3-phosphate all the way to pyruvate, right? And then up here, let's not forget that we said that we're using 2 molecules of ATP, right? So remember, we're using 1 molecule of ATP right here between glucose to glucose 6-phosphate, and then we're using 1 molecule of ATP from fructose 6-phosphate to fructose 1,6-bisphosphate, right? If you can see it, it's right here. So that's 2 molecules of ATP being used, but then we're producing 4 ATPs. So 4 minus 2 would be a net of making 2 ATPs in glycolysis. So we're making a total of 2 ATPs in glycolysis. And that's not a lot of energy at all, okay? We make like 34 to 38 ATP per molecule of glucose in the electron transport chain, which we'll discuss later, all right, in another video. And then we're making 2 NADHs, right? We're releasing out 2 H2Os, 2 water molecules. All right, I'm just trying to list the important things here. And and that's pretty much it. Oh, and the final product, which is the most important, we make 2 pyruvates. That was the whole goal. We can't forget that, right? We make 2 pyruvates. And then, of course, everything here we see, like starting from here, phosphoenol pyruvate is not 1, but 2, because everything is happening twice. We have to remember that, because dihydroxyacetone phosphate is also getting converted to glyceraldehyde 3-phosphate via triose phosphate isomerase, and then it's happening again. Okay, so instead of 1 2-phosphoglycerate molecule, we have 2 2-phosphoglycerate molecules. Instead of 1 3-phosphoglycerate molecule, we have 2 3-phosphoglycerate molecules, right? Instead of 1 1,3-bisphosphoglycerate molecule, we have 2 1,1,3 or 2 1,3-bisphosphoglycerate molecules. All right, I know this is kind of redundant or repetitive, but this is what happens in your body. All right, instead of having 1 glyceraldehyde 3-phosphate, we have 2 glyceraldehyde 3-phosphates. All right, and that's it from there to there. And also one thing to note is that all the way, so everything that's happening, right, from glyceraldehyde 3-phosphate, so let me go and write this down. Everything that's happening from glyceraldehyde 3-phosphate, everything from glyceraldehyde 3-phosphate all the way down to phosphoenol pyruvate, all those reactions are reversible, so it can go back up. Okay, so all the reactions involved here are going to be, write it in red because it's important, reversible. Okay, and one more reaction that's reversible, or two more actually, are it's going to be the reaction involving aldolase. All right, so let's go ahead and see what I mean by that. So you see this reaction right here where fructose 1,6-bisphosphate got split by aldolase into glyceraldehyde 3-phosphate and then into dihydroxyacetone phosphate. That reaction is reversible, so it can go back. All right, so glyceraldehyde 3-phosphate and dihydroxyacetone phosphate can get converted back into fructose 1,6-bisphosphate. All right, and actually there's one more step that's reversible, which is the step between glucose 6-phosphate to fructose 6-phosphate. So this reaction right here, guys, from glucose 6-phosphate to fructose 6-phosphate is reversible. It can also get converted back into glucose 6-phosphate, all right? So it can go from glucose 6-phosphate to fructose 6-phosphate, but it can also go from fructose 6-phosphate back to glucose 6-phosphate. All right, so that was a lot, right? And that's pretty much it. That's glycolysis for us, right? We produce 2 pyruvates at the end, and if the conditions are aerobic, these 2 pyruvates will go and get converted into acetyl coenzyme A and then go to the mitochondria and start the Krebs cycle and electron transport chain to produce our massive amount of ATP if there's oxygen present. All right, if there's an adequate amount of oxygen present. But if it's an anaerobic condition, then these 2 pyruvates will actually get converted to lactic acid, all right, which can then get, converted to lactate and go into the liver for energy. And this one other thing to relate, if it's anaerobic, is pretty much when you're exercising, right? So let's say you're doing the bench press or something, and you're feeling that burn. That burn is because these 2 pyruvates aren't going to the mitochondria anymore, right? They have to be converted to lactic acid, which is the burn you feel, right? The acidic conditions. So it's going to be converted into lactic acid when it's anaerobic conditions, all right? These pyruvates. And the lactic acid you can use short-term for or not for short, but for energy and glucose, right? And via the liver. Right, so it's going to go to the liver. And you can use that as energy while you're working out, right? Oops. All right. So that concludes our video for glycolysis. And I really hope that made sense, right? Remember, you can't forget about the magnesiums, right? I said that in the previous video, that in every reaction where you see an ADP or ATP or NAD plus involved, we use magnesium. So let me just point that out here before we go. So when we use NAD plus to NADH in this reaction right here, from glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate, we also use magnesium. All right, so let me go ahead and write it down here because there's no more room there. All right, so when we go from glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate, right? 1,3 bis-phosphoglycerate we use, along with everything we said, right? Our glycerol halide 3-phosphate dehydrogenase. We also need the help of, actually, let's write in a different color. We also need the help of magnesium to carry forward this catalyzation reaction, all right? With the help of the enzyme. Remember, the enzyme is the most important, but magnesium also helps convert from glycerol halide 3-phosphate to 1,3-bis-phosphoglycerate. All right, and then from 1,3-bis-phosphoglycerate to 3-phosphoglycerate, right, we also use magnesium as a helper to convert from 1,3 to 3-phosphoglycerate, right, 1,3-bis-phosphoglycerate to 3-phosphoglycerate, because we make an ATP here, so phosphoglycerate. And then from when we go from phosphoenol pyruvate to pyruvate, so actually I think we have room down there to write this down there so we can actually see it. Yeah, there you go. When we use pyruvate kinase, we also have the help of magnesium right here. All right. So as you can see, magnesium is used a lot in breaking down sugar and trying to convert it to energy. So it's an important mineral that we use. All right. And now that concludes glycolysis, and I hope it wasn't too confusing, right? It might have been, but just try to go over this video like over and over until you have it down, all right? And I hope to see you in my future videos. Don't forget to like and subscribe and hit that notification bell so you know when I publish my future videos, all right? See you guys.